Today we're doing a deep dive into malaria control, but we're moving past, the usual chemical insecticides that are just not working as well anymore.
Yeah.
Our sources lay out this really fascinating mathematical model. It basically weaponizes a new biological agent, a transgenic fungus.
That's the one. Metarhizium pingshaense, or med hybrid for short.
And the target is the Anopheles colucii mosquito, which is a huge problem in places like Burkina Faso.
Exactly. And our mission here is to look at this model and see what it tells us about the real population level impact. The whole strategy is, well, it's basically a Trojan horse.
A Trojan horse.
You release male mosquitoes that have been exposed to this fungus. It's a fast-acting, toxin-producing one. And the math is supposed to tell us if this can actually knock down the wild population.
Okay, so how does that work in practice?
Yeah.
And why only the male mosquitoes?
Well, the beauty of it is that the male is just the delivery guy. He's the vector. He gets released. He finds a wild female. They mate. And during that process, he passes on the met hybrid fungus. And it's lethal. The model shows it works pretty fast. The average time for about 80% of them to die is around 5 days.
5 days. So she dies before she has much of a chance to spread malaria.
That's the idea.
That sounds really promising, but I imagine the logistics are demanding.
Right.
What did the model say about the kind of effort needed to actually see results?
This is where it gets pretty staggering. To hit an 86% reduction in the local female population, you need to release 10 fungus-exposed males for every single wild mosquito.
10 to 1.
10 to 1 every 3 days. And you have to keep that up for 6 months.
6 months, 10 to 1 every 3 days. I mean, that sounds like a logistical nightmare. Does the model say that's even realistic compared to something like a gene drive?
It definitely highlights the operational hurdle.
Mm-hmm.
And if you're aiming for that bigger global health target, a 90% reduction, it gets even tougher.
How much tougher?
Daily releases at a 6 to 1 ratio for about 5 months straight. So the takeaway is clear. High frequency and high volume are absolutely critical.
Okay, so the effort is massive. But what I found really surprising was that the model showed even that enormous effort is totally wasted if one very specific biological condition isn't met. What was that?
Yeah, this was the real kicker. The fungus absolutely cannot establish itself in the population based on mating alone. It just can't.
At all?
Not at all. Without transmission from the colonized cadavers, the dead bodies, the whole thing just stops. The basic reproduction number, R naught, it drops to 0. The fungus gets eliminated.
0. Wow. So mating isn't enough to keep the cycle going. Why is that cadaver pathway so biologically crucial?
It all comes down to the females. Anopheles colucii females, they're typically, they're one and done. They mate only once in their lifetime.
I see.
So an infected male can pass the fungus to a female, sure. But she doesn't then go on to create more infected males. The fungus just hits a dead end with her.
Right.
The cadaver is what closes the loop. A susceptible male has to come into contact with a dead, sporulating body to get infected. That's what keeps the cycle going among the male population.
So what's the big takeaway here for control efforts? It sounds like this fungal program, even with all the challenges, could be a really viable alternative to something like a gene drive.
It could, yeah. Especially in places where there are, regulatory hurdles or public acceptance issues with releasing genetically modified mosquitoes.
It's another tool in the toolbox.
A powerful one.
Okay.
But it leaves us, and it leaves you, the listener, with a really important final thought.
Okay.
This whole model hinges on cadaver-mediated transmission. But that's something that hasn't really been documented reliably in semi-field settings. Why? Because things like ants. They find and scavenge the dead mosquitoes really, really quickly.
Before the fungus can even sporulate and spread?
Exactly. So the question is, what kind of research or what kind of innovation do we need to make sure this absolutely critical transmission loop can actually work in the real world? The model says it has to happen, but nature might have other plans.